video is all about using U substitution to help you find the integral of something, which is something you do in Calc 1. It's a pretty important concept, so here we go. Alright, when we're using U substitution, we're trying to pick something in our integral to make U equal so that when we take the derivative of it, that will match something else in our problem. So one thing is if a problem has parentheses, there's a really good chance that what's inside the parentheses is what U should equal. So in this case, we're going to make U equal x to the fifth plus 3. Then we're going to take the derivative of x to the fifth plus 3, which that's where we multiply by the power and subtract 1 and get 5x to the fourth. The plus 3, that part is 0 when you take the derivative, and so that ends our derivative. And what we do instead of writing du over dx, kind of like dy over dx, is we put the dx over here on the right side. What we're looking for is what we have that's not a part of U, like this is U inside of our parentheses, so this integral is going to be U to the fourth. But what we want to do is compare the other things, the 10x to the fourth and the dx, to this. And we're going to say, well, those are really close, but they're not the same. And so since they're not the same, we're going to divide them. If I do 10x to the fourth dx divided by 5x to the fourth dx, everything except the 10 and the 5 cancel, and the 10 and the 5 actually end up making 2. And so the idea is that we're replacing 10x to the fourth dx with a 2 and then the other side of this, which is du. And so the reason we have to do that second part is because we can't leave the 10x to the fourth dx here and take the integral, because then we'd have too many letters and it just wouldn't work out. So we have to switch the dx to a du. We do that by comparing these. Now we need to take the integral of this. And since this is something to a power, we're going to use the power rule. The power rule is where we add a power and then divide. It's the exact opposite of what we did up here when we took the derivative. 2u to the fifth over 5, we're going to put back in what u is, so that's 2x to the fifth plus 3 to the fifth over 5. We can write it like that, or you can move the 2 and the 5 in front and make it be 2 fifths x to the fifth plus 3 to the fifth. Either way, we need a plus c because it's an indefinite integral, so we don't know what other constant could be there. So we put plus c to represent that. So in any of our indefinite integrals where we're not plugging in numbers, should have a plus c. So this next one is similar. We're going to take what the parentheses is, and we're going to set u equal to it. So I'm going to take the derivative, and so multiply by 5 and then subtract 1, which gives us 15x to the fourth dx. Now I'm going to compare that with what I have. They match completely, and so I'm just going to have du. I'm not going to have an extra number. Then since this is u and then it's to the negative fourth, this is u to the negative fourth du. To take the integral of this, we're going to use the power rule. So I'm going to add 1. Negative 4 plus 1 is negative 3. And then I divide by negative 3. Make sure you divide by not just 3, but also a negative, because that makes this be negative 1/3, 3x to the fifth plus 4 to the negative 3. But a lot of times in math we say, well, I don't want negative exponents, and so to fix that negative exponent, we would write it on the bottom of a fraction, and since there's already a 3 on the bottom, it's just going to go in front of that. So that that's not supposed to be a 3. And since we put it on the bottom of our fraction, now it's a positive third power. So depending on who your teacher is how they would rather you leave it. They would rather you leave it to negative third. That's fine. If they want you to move it to the bottom, that's technically a slightly better answer. You just need to make sure that you know what they want. I personally want it to be on the bottom, but hey, it's whatever. On this next one on number 3, same idea. We have parentheses. The parentheses are on the bottom, but we're still going to say that u is what is inside those parentheses. And so one of the things with this is that somewhere along the way, we need to think about, if I put u here, what does that give me? Well, it gives me a u cubed on the bottom of my fraction. I compare the 60x to the 4th dx and the 20x to the 4th dx, and I divide them and get a 3, which will be on top du. Now, in order for us to take the integral of this, we need to move the u cubed up to the top, making it have a negative exponent. So the opposite of what I just did on the last problem. Moving it up to the top, though, we haven't actually taken the integral. And so this is where I say I can use the power rule. I can add 1 and divide by whatever I get. So that's 3u to the negative 2 over negative 2, which if I move the u to the negative 2 down to the bottom and put u back in, that gives me 3 over 2 4x to the 5th minus 1 to the 2nd power on the bottom plus c. On number 4, we're going to set the inside of the parentheses equal to u. Get x squared minus 5 du equals 2x dx. And so we compare 4x dx and 2x dx. We divide those and we get 2. So this is 2u to the 3/2 du. Now this is still a power rule because I'm going to add 1 to this exponent. Well, if I add 1 with a fraction, I need a common denominator. So I really want to add 2 over 2, which is going to give me 2u to the 5/2. I'm going to divide by 5/2, and this is where it can be a little tricky. I think the whole common denominator thing's not so bad, but how do I take 2 and divide it by 5/2? Well, I have to flip the second fraction so that I do 2 over 1 times 2 over 5, and I get 4/5. So this is going to be 4/5 x squared minus 5 to the 5/2. $15 is the same kind of problem, it's just written a different way. This square root symbol, the other way of writing a square root is to write it to a fractional power. A square root is a 1/2 power. Cubed root, where there would be a 3 right here, would be 1/3. Fourth root would be 1/4, and so on. And so now that we know that, this is just a problem basically like number 4 was. So u is what's underneath our square root, which is x cubed minus 4. du is 3x squared. And so we compare 15x squared and 3x squared. We divide them. Make sure you are always doing what we originally had in the problem divided by what you got. And we get 5u to the 1/2. We're going to add a power, so we're going to add 2 over 2, which gives us 3/2. And we divide by 3/2. So this is 5 over 1 times 2/3, which is 10/3. So 10/3 x cubed minus 4 to the 3/2 plus c. Now that's actually the end of the ones that are power rule here. On number 6, there aren't any parentheses. And so the trick we've been using where we're looking for parentheses to figure out what to make u equal doesn't work. And so we have to think about our other condition for u, is that u needs to be something that when I take the derivative, that shows up somewhere else in the problem. So that means that u should be x to the 5th minus 3, because when I take the derivative and get 5x to the fourth, there is an x to the fourth somewhere else in our problem. If u is x to the fifth minus 3, that means u is going to be on the bottom of our fraction, and on top is whatever 10x to the fourth divided by 5x to the fourth is, which is 2. Now, if you try to power rule 2 over u, you run into some problems and end up dividing by 0. Whenever you have just a regular u on bottom, this is a natural log problem. This is 2 natural log of the absolute value of u. Then we put back in what u was and get 2 natural log of x to the fifth minus 3 plus c. But it's really important that you're looking out for those problems where all of a sudden there's not parentheses on the bottom with the power. That would be different. That's where we move it up to the top and use the power rule. And since that's not what's happening, we're going to have to use the natural log rule when we integrate. Okay, if I have an e, then what I should make my u equal is the exponent up here. So u is 2x to the fourth plus 1. Du is going to be 8x cubed dx. I have 32x cubed and 8x cubed, which is going to make 4. Then since u is 2x to the fourth plus 1, and I have e to that, then this is e to the u du. U just is wherever it's supposed to be in the problem. This one away, because of the 8x cubed, we put a 4 in its place. So then I have to say, well, e to the u is what I get because u is 2x to the fourth plus 1. This is easy because it's e for easy. If I have 4e to the u and I integrate it, I get 4e to the u. And so then I just say, well, that's 4e to the 2x to the fourth plus 1 plus c. On trig functions like this, then we have parentheses, so that's a good clue that you want to make your parentheses be u again. But also it's going to be the inside of one of our trig functions probably. Now, depending on what we have, it can be more complicated what u is or whatever. So the important thing is to pick something and try it, take the derivative, and see if that thing shows up somewhere else in your problem. Like we have x to the fourth here, x to the fourth here, so we picked the right u. Negative 125 divided by 25 is negative 5. So this is negative 5 secant squared u du. The integral of secant squared is tangent, and since this is negative to start, it'll be negative in my answer, because secant squared is not one of them that switches signs. So this is negative 5 tangent u, which is negative 5 tangent 5x to the fifth plus 3 plus c. And here's another trig function one. Now, this time we have 2 sets of parentheses, but they're both the same, which is important. Like, that actually has to be the case for this problem to work out right. If u is 3x squared minus 1, du would be 6x. And so, dx. We're going to do negative 24x divided by 6x and get negative 4. Negative 4 cosecant u cotangent u du. And so that's good that that happened, that these were both used, because this is how we're going to be able to take the integral. The integral of cosecant u cotangent u is negative cosecant u, and so since our answer is negative and there's a negative in front here, that makes it switch signs so that it's positive for cosecant u, and then we input the parentheses back plus c. It's really important that when we're integrating our trig functions, we know which ones are supposed to switch signs and which ones are not supposed to switch signs. So cosecant cotangent switches to negative cosecant, but if it's already negative, like in this case, then we take the negative off because it's like it's canceling. All right, now we're going to do some more U substitution, but they're a little trickier. There's a little bit more complicated stuff going on, and so U is actually provided for us on this. So if we know that U is e to the 5x plus 2, then we're going to find the derivative. And so let's remember our derivative rules for things like e to the 5x. We have to do e to the 5x times the derivative of 5x, which is 5. So 5e to the 5x dx, which is what's in front here. And so that'll go away. And since this inside of our parentheses is u, this is u cubed du. So this is the power rule. And so I know it's the power rule because it's something to the third power. So we'll do u to the 4th over 4 and then change back into what u is. So e to the 5x plus 2 all to the 4th over 4 plus c. Or you can put it as 1/4 in front of your parentheses, whichever, doesn't really matter. On 11, e to the 2x plus 3 is u, so u is the bottom of the fraction. Du is 2e to the 2x dx. And so we're going to compare the negative 4e to the 2x that's on top with this 2e to the 2x. When we divide those, we get negative 2. What u is on the bottom, so that's over u. Remember, if it's over u and not over u squared or over u cubed or something like that, this is a natural log problem. So this is negative 2 natural log of u, which is negative 2 natural log of e to the 2x plus 3. Now I'm putting absolute value bars around this to be cautious, because the reason for those is you can't plug negative numbers into a natural log and get an answer. So if I had natural log of x, I would be saying, okay, I'm going to change all the negatives into positives. Just so you know, like, these absolute value bars could be parentheses easily on this problem, because e to the 2x plus 3 will always be positive because of how e functions work. So if you were thinking that hey, I don't know that those really need to be absolute value bars, you're right, they don't. They can be regular parentheses there, but you do need something there. You can't just not have any grouping symbol at all. 12 says u is sine x, so the derivative of sine x is cosine x. And so that's up here at the front of my problem. I have negative 2 cosine x that I'm comparing to regular cosine x. And so that's going to give me negative 2. U is sine x, and that's in the exponent for e. So this is going to be e to the u du. Now if I integrate negative 2e to the u, that's negative 2e to the u. And then I put u back in, so negative 2e to the sine x plus c. Looks kind of messy. If I take the derivative of 5 plus ln of 5x, the 5 part goes away. The derivative for a natural log is 1 over u times u prime. In this case, u would be 5x, so we'd do 1 over 5x, but then we'd times it by the derivative of 5x, which is 5, which means our 5's cancel. And so the derivative of ln of 5x, or ln of any number times x, is 1 over x. That 1 over x has to do with the fact that this has an x on bottom. Basically, we're comparing 2 over x and 1 over x and saying if I divide those, I'm left with a 2. So this is 2 cosecant squared u du. I have to think about what the integral of cosecant squared is. It's negative cotangent, and so this would be negative 2 cotangent u, and then I put u back in, so negative 2 cotangent 5 plus natural log 5x plus c. Evaluate each definite integral. You will need to use U substitution. And so we're going to do the same thing we've been doing, where we pick U. We're going to pick what's in parentheses most likely here, and then find du and get 2 times 3 is 6x squared dx. We're still going to say, all right, what's 18x squared divided by 6x squared, which is 3. This is u, so this is u cubed. But the difference is, we can do this one of two ways. I can plug 1 and 0 into u and write those bounds here on my integral, and then I won't have to switch back to x's later. Or I can integrate this, put u back in, and then use my original numbers. The way we've gone over in class is to do where we're going to plug in 1 and 0 right now and say 2 times 1 cubed minus 2 times 0 cubed minus 2. And these are going to be the numbers I write on my new integral. So that's 2 minus 2, which is 0, 0 minus 2, which is negative 2. So 0 and negative 2. And so what we do is we integrate this like normal. So I add a power and divide. And then this is where we draw the line and we say, let me plug in 0 and negative 2. So I have 3 times 0 to the 4th over 4 minus 3 times negative 2 to the 4th over 4. Well, the first part of that is just 0. And then if I work out this other part, this is 16 over 4, which is 4 times 3, which is 12, which gives me a negative 12 for my answer. On 15, u is going to equal the 4x squared plus 4 that's in our parentheses. So du is 8x. 24x and 8x leave us with a 3. We can either write this as 3 over u squared, or we can say, oh, well, I know I'm going to have to move the u squared up to the top so that I can integrate. And then we need to change 3 and 1. So we need to do 4 times 3 squared plus 4, and 4 times 1 squared plus 4, and see what we get. So that's 9 and 36 plus 4 is 40. This is 4 plus 4, which is 8. So we have not yet used the power rule to integrate this. I'm going to add 1 and get negative 1, divide by negative 1, and then I'm going to plug in 40 and 8. Now, if we're going to plug this into the calculator, you can plug it in with the u to the negative 1. If you are trying to do this like on your own, then you would want to move it to the bottom and make this be like negative 3 over u before you actually start plugging it in. Either way is fine by me. I am not sure where a calculator is near me, and so this would be negative 3 over 40 minus a negative 3 over 8. Well, we've got a little change happening right here. And I need a common denominator if I'm being lazy and not looking for a calculator, so that I get 15 over 40 minus 3 over 40, which is 12 over 40, which I can simplify by 4 and get 3 over 10, which as a decimal is 3/10. LOL, I have a calculator right next to me. Hang on. Okay. On These next ones, where we have trig functions, I'm going to be using the unit circle to finish the problem off so that I can get answers like square root of 3 over 2 or square root of 2 over 2 or things like that, which means I won't have rounded. So keep that in mind that we'll be doing that. If I want to use U substitution here, U is going to equal the 2x inside of my trig function. Du is going to equal the derivative of 2x, which is 2. So I'm going to do negative 4 divided by 2 and get negative 2 sine u du. If I plug in pi over 4 and 0 where x is, that's 2 times pi over 4, which is like 2 over 1 times pi over 4. If I do that, the 2 and the 4 will cancel and give me pi over 2. And then 2 times 0 will give me 0. So that's pi over 2 up here at the top, 0 at the bottom. Now I'm ready to integrate. So I have to say, well, what's the integral of sine? The integral of sine is negative cosine. And so since it's already negative, that's going to cancel out and give me 2 cosine u. And I'm going to plug in pi over 2 and 0. So that's 2 cosine pi over 2 minus 2 cosine 0. If I'm using the unit circle, then I'm looking for my x value at pi over 2 and my x value at 0. So here's a unit circle, and my x value at pi over 2, which is up here, is 0. My x value at 0 is 1. So the x value at pi over 2 is 0. X value at 0 is 1. So 2 times 0 minus 2 times 1 is just negative 2. On 17, u is 4x and du is 4dx. And that means the 4's will cancel, and this is going to give me secant squared u du. I'm going to plug in pi over 4 and pi over 6 into this 4x. So 4 times pi over 4. The 4's cancel and give me pi. 4 times pi over 6. 4 over 6 can cancel and give me 2 over 3. So my bounds are pi and 2 pi over 3. We want to integrate secant squared u, and we get tangent u. And we're going to plug in pi and 2 pi over 3. So tangent of pi minus tangent of 2 pi over 3. Tangent on the unit circle is our y value over our x value. So at pi, our y value over our x value is 0 over negative 1. 0 divided by negative 1 is just 0. At 2 pi over 3, which is up here, our y value is square root of 3 over 2. Our x value is negative 1/2. So I'm going to put square root of 3 over 2 over negative 1/2 and simplify that. And so the first part of that is 0. These negatives cancel and give me plus. When I'm dividing these two fractions, the 2's will cancel, leaving me with square root of 3 over 1, which is just square root of 3. 0 plus square root of 3 is just square root of 3. 18 is a bit more complicated. Not a whole lot, but at least a little. U is what's inside, which is 2x minus pi over 4. Du is the derivative of that, which is just 2, because the derivative of pi over 4 is 0, because pi over 4 is a number and doesn't have an x with it. Negative 4 divided by 2 is negative 2 cosine u du. And we're going to plug in pi and pi over 2 where x is. So this is a little tricky. 2 times pi minus pi over 4, or at least it can be tricky. We'd actually use our unit circle to help us with this. If I have 2 pi and I subtract pi over 4, 2 pi is the same as 0. If I subtract pi over 4, I'm going backwards pi over 4, which gives me 7 pi over 4. The other way of thinking about it is to get a common denominator. So if I have 2 pi over 1 and I want a common denominator, I times the top and the bottom by 4. So I need 8 pi over 4 minus pi over 4. So that's the other way of getting 7 pi over 4. When I plug in pi over 2, that's 2 times pi over 2 minus pi over 4. These 2's cancel so that I get pi minus pi over 4. Again, you can use the unit circle, look at pi, and then go backwards pi over 4, or you can get common denominators, or you can just think 1 minus 1/4 and get 3/4. So this is 3 pi over 4. That's our two numbers that are going to go up here. And so now we're ready to integrate. So negative 2 cosine u, the integral of that is going to be negative 2 sine u, because the integral of cosine is sine. Then we're going to plug in 7 pi over 4 and 3 pi over 4. So negative 2 sine 7 pi over 4 minus a negative 2 sine 3 pi over 4. If I look at my unit circle, sine is my y value. 7 pi over 4 is down in the bottom right quadrant, which is negative square root of 2 over 2. If I do sine of 3 pi over 4, 3 pi over 4 is in the second quadrant, and it's my y value, and it's positive square root of 2 over 2. So be careful here. You might accidentally think these cancel out, and they don't. The 2's here and here, here and here cancel, giving me positive square root of 2 plus another square root of 2, which gives me 2 square roots of 2 for my answer. 19. So we're back to indefinite integrals, and these are not going to require U substitution. So like here, the tricky thing is I'm going to use the power rule and add a power. So I'm going to do plus 3 over 3 on this first one, and that's going to give me 7 over 3. So this is the number that starts off in front, 7/3. I'm saying that now my exponent is 7/3, which means I need to divide by 7/3, which means these will cancel, and I'll just have x to the 7/3 in my answer. And we're going to do the same thing with each of these other two terms. So add 4 over 4. So I need to divide by 5 over 4. Well, that cancels. So this is plus x to the 5/4. Add 5 over 5, and I get 6 over 5. If I do 30/5 divided by 6/5, the 5's cancel, and I do 30 divided by 6, which is 5, x to the 6/5 plus c. On 20, these are negative exponents. We're going to add 1 and then divide, and so that's 2x to the negative first divided by negative 1 minus 15x to the negative third divided by negative 3. Now, be careful here, because we want to divide, so this gives us negative 2x to the negative first, and positive 5x to the negative third, and then we're also going to move the x's down to the bottom so that they have positive exponents, because we like that in math for some reason. So this is negative 2 over x plus 5 over x cubed plus c. On 21, this is a trig function. Couple problems. It's on the bottom of our fraction, and it's sine squared, and we don't know the integral of sine squared, or at least not off the top of our heads probably. So one thing that we're going to do is use an identity, because if I have sine squared on the bottom, I can change that into cosecant squared on top. Now that's helpful because now I can find the integral of cosecant squared. The integral of cosecant squared is negative cotangent. Since it's already negative, that's going to make it positive 3 cotangent x plus c. So remember, we can use trig identities to change it to something that we know how to take the integral of. But if you do that, you're not done until you actually have done more than just used an identity. On 22, this matches up with the inverse tangent formula. So the integral of u prime over 1 plus u squared is the inverse tangent of u plus c. And so the reason I know it's inverse tangent and not one of the other ones is there's no square root on the bottom. Now, what we're trying to do is figure out what u has to be. And so to do that, we need this 9 to be a 1. So I'm going to take out a 9 on bottom. And if I do that, that means I'm taking a 9 out of something that doesn't have a 9, which makes it be x squared over 9. This tells me what u squared is. And so if that's what u squared is, then u is the square root of that, which is x over 3. The derivative of that, which I can call u prime, since u prime's in my formula, is just 1/3, because it's the number that's next to x. And so then I say, well, there's not a 1/3 on top, like there's supposed to be. Let me put a 1/3 on top, which means I also have to multiply the bottom by 1/3. The reason we're doing this is because we're trying to basically say, all right, what is a part of my formula and what isn't? I can do 1/3 times 9 and get 3 on the outside. And so the part of this that is my formula is u prime over 1 plus u squared. So the 1 over 3 that's in front needs to go in the front of my answer because it's extra. This is 1/3 inverse tangent of x over 3 plus c. Now let's switch back to some more definite integrals. So good thing I found my calculator for 23 because this one's going to be a bit of a doozy. We're doing x to the 5th over 5 minus 2x cubed over 3 plus x squared over 2 plus 2x. Make sure you remember that the integral of a number, you have to put an x with it. We're going to plug in 1 and negative 1. And so I do 1 to the 5th over 5 minus 2 times 1 cubed over 3 plus 1 squared over 2 plus 2 times 1 minus negative 1 to the 5th over 5 plus 2 times negative 1 cubed over 3 plus negative 1 squared over 2 plus 2 times negative 1. Now, all these negative 1s that I have in parentheses, that's kind of a big deal. If you plug this into your calculator without those parentheses, it is not going to tell you the right answer. Even though I have my calculator, like, I feel like it'll be faster to do this by hand. Like, this is 1/5 minus 2/3 plus 1/2 plus 2 minus, this is negative 1/5, that's minus 2/3 plus 1/2 minus 2. This negative is going to switch all of these signs. So this will be plus, plus, minus, plus. So the only thing that cancels are the 2/3, or wait, maybe these cancel also. And we get 1/5 plus 1/5, which is 2/5, 2 plus 2, which is 4, which is 4 2/5. I am not super confident that that is the answer because it's really easy to make a mistake on this. Don't worry, I figured it out. That was supposed to be a negative, which would make this be, originally it would have been a positive, and then we would have switched it to a negative. And so the negative 2/3 don't cancel out. They come together to be negative 4/3. So now I am going to use my calculator so that I don't have to get common denominators, although it wouldn't be that bad to get common denominators if we wanted to. This is 3.06 repeating, so 3.067, or if you did try to get it as a fraction, that should be 46/15. That's, I believe, the right answer. So sorry about that little mess up, but that's the really frustrating thing about this is like the calculus of it was fine. I just forgot a negative, which is an easy mistake to make. So the problem with math is you want to make as few of those little mistakes as possible, obviously, because every time you make a little mistake like that, it kind of affects your grade. So 24, -3/x, that's a natural log. So -3 natural log of the absolute value of x. We're going to plug in -1 and -4. So this is -3 natural log of -1 minus a -3 natural log of the absolute value of -4. So the natural, like the absolute values are going to change those to positive. So when I type this in my calculator, this is -3 ln of 1 plus 3 ln of 4. So I get 4.159 for my answer. Finally, the integral of -2e to the x is easy for e, or e for easy. So -2e to the x, and I'm going to plug in 1 and -3. So that's -2e to the first minus a -2e to -3. Now, we can do some things to this, like move this down to the bottom and get a common denominator. And so that common denominator would be e cubed, which gives us -2e to the fourth plus 2 over e cubed. If you were having to do a problem like this without your calculator, that's probably how you would want to write your answer. But if you have your calculator, you can just type this in and get something like -5.337. And there you have it, folks.